on the fourth, so here we call him Farron, and then other guys as well. So what we're trying to do is to translate the knowledge in data science and all the tricks in cargo into this AI platform we call Driverless AI. And then you have myself here, and we're trying to catch up with them when I have time, but I'm still too far away from them. Okay, so last time when I came to Glassdoor, talk about the open source of H2O product. I'm sorry, let me go back. So you see that all the products here with the white background, they're like the open source H2O product. So we have the original H2O open source machine learning platform, and then when you package it with Spark, we have the sparkling water, which you can run H2O on Spark. And then now we're trying to move on the algorithm from CPU-based to the GPU-based. So that's why we have the H2O for GPU. That's our next generation of the open source H2O algorithm. And all this here, so because we've been doing this for quite a few years now, so we got all the feedback from customers, so we can see the actual demand, what kind of things that we actually need to give the customer to use. So we packaged it all up and built in the feature engineering and all other cool stuff into this software we call Driverless AI, which is the main focus of today. Have anyone tried this before? This is software. 1, 2, okay, cool. Okay, again, before that, let me just bring up about the customers or communities. So we have open source community here. We have a lot of people using H2O for free because they just know how to do it. But some of the customers, they come back to us because they want us to help them productionize H2O, so to maybe just help them to understand what kind of business problem they need to frame as machine learning problems and put that into productions. And that's why we have a lot of different customers across different sectors. So today we talk about financial sectors, but H2O is a generic machine learning platform, so you can actually use it as long as you can frame a business problem for machine learning. So it's across financial, insurance, healthcare, retail, everything that you can think of, we can do it. Just a few more marketing slides, and then I'll be done, right? So these are some of the partners. So you can see you can if you have been using different cloud solutions, we can find H2O as like a marketplace. You can find H2O already there in different cloud provider. We work really closely with NVIDIA and IBM because they have the GPU power. So we're trying to work with the hardware to make sure that is optimized for the big GG Xbox and the Power 9 systems. And we also have other partners about the data ecosystem as well. So these are some of our partners. And just one more thing about the H2O. So this is from the Gartner. So Gartner, every year they try to look at different the top companies in the industry. So this is looking at the data science and machine learning platform market. So we're saying that we're trying to use the customer feedback, the feature of the software, and all the other different factors to come up with some points about different companies and their positions in the market. So we are lucky to be recognized as one of the leaders. You can see on the top right corner. And then this is one of the big things for us, which happened a few months ago. Okay, so back to today's topic. So why do we create this software, Driverless AI, for the market? So the first reason is that we understand there's a lack of good data scientists in the market. So even though you say that you have a lot of market students or people studying data science coming out from universities or coming out from other companies, we still have a lack of data scientists in the market, and that's quite real. So I think Michael and David should know because they're trying to fill up the headhunter. So they try to fill up the market with data scientists. And it's super hard to find the right people for the right company. And so that's why we're trying to create a software that kind of bridge the gap between the shortage of the data scientists and the actual business users. And what happened now is that we're trying to use what we learned from the Kaggle Grandmaster, so all the top data scientists in the world. We use Kaggle as a benchmark. We use the knowledge in data science to try to translate all the tricks they had in the past many years, put it into an AI platform we call Driverless AI. And many people, junior data scientists, expert data scientists, any kind of data scientists, they can use this software to accelerate their workflow. So we try to optimize it with GPU. So some of the algorithms they can run quickly on GPU. We optimize the pipeline, so actually can create a smooth pipeline from data feature engineering to model stacking to all the things that you want to do for scoring into one single pipeline, which I will show you in a live demo later on. So that will save you time to put different teams together, put different data engineer teams, data science team, and a production team together to create a pipeline. So this software can do that for you. So it's like AI to create AI. So to be more specific, so this is like a workflow that we will have, maybe not a specific workflow for you guys, but this is a typical workflow for data science in most of the enterprise organizations. So we start with some data integration. So we have different data source on the left-hand side, but we don't have with this. So we still ask the users to provide their own solutions to figure out the first table. So we want to have the first table for machine learning. Then you have some features and the target. So we don't have with that. But after you have the first table, after you have the table for machine learning, then we can do the rest of the pipeline for you with this software. So starting with some check of data, so we check the data quality check, and then we have some transformation about preparing the data for machine learning, and then we have some feature engineering stuff from the Cargo Grandmasters. So after that, we test different new features, create different models together, and do an ensemble together. And finally, we create a model that you can export into a pipeline that you can use in productions in one go. So the second half of the pipeline is all automated with this software, Driverless AI. So I talked about Professor Lillian Wilkinson earlier. So he's the father of graphics, right? So he's now working at H2O to optimize this for us. So this is the smart or automatic visualizations in Driverless AI. So this is the step before you train the model for machine learning model. You want to have a look at it, the data first before you do anything. For example, you can look at the outliers, look at the other distribution of different features before you decide what to do with the data set. So this is something that I will show you in a live demo that's super useful. You just drop in the data and it will create the most interesting graph for you automatically in the software. So after you're happy with the data, then you can start using the Grandmaster recipes, we call it, to transform different features into new, more powerful, more predictive features for machine learning purposes. So for example, we have all different tricks they learned from Cargo in different Cargo competitions, like how to transform a target, how to transform different features, different tricks that you may not usually do it manually even if you have the time to do it. So we try to automate this step so people can just spend the time thinking about the business problem and how to present the result, rather than just try to figure out how to feature engineering different steps to squeeze the best of the data. So that's one of the things that we automate in Driverless AI. And so after we have the features, we also use different things to evaluate the metrics, evaluate the performance of different features. So we don't use all the features we create from the previous step, but we just get the best features. So it's like feature selection step to get the best features, the best new features, and use that to create the last model, the last ensemble using different algorithms. That's how we get to a good accuracy. For example, we can use the Cargo, again using Cargo competition as a benchmark. So for example, the BNP is a bank in France and other places in Europe. So we use one of the past competitions as a benchmark for Driverless AI. So we see how can we compete with the best team like 2 years ago. So this team you see in the top 10, they spend months to get to that positions. They try different tricks, different feature engineering, different kind of stacking process to get to the top 10. But we're saying now, because we have the Grandmaster recipe in Driverless AI, we can actually automate that in a few hours. So we drop in the data, let it run for a few hours, and we can get close, really, really close to the top 10 people, top 10 team in that competitions. And that also includes I think 3 of them are actually working at H2O. So we're trying to compete with the best of them in the past. And that actually gives us a lot of different kind of business advantage, because now you think about you have different data going into your organizations, you have different questions to ask, you have different business problems to solve. If you ask the team, like the best team in the world, to spend a month on just one problem, you will never have enough time to get to the answers for business needs. But now we're saying that we can use this software to get to almost the same level of the Cargo Grandmasters within a few hours if you have the GPU and our hardware in place and this software. So that's about so how we benchmark the accuracy. But sometimes this is not just enough because some people would like to explain the model, because for GDPR and for many other reasons. So your customers, your colleague, or your boss, they may want to understand what is the model doing actually? So what are the input contributions to the outcome? For example, how if you have a customer coming back to you asking you, why do you give him or her the premium insurance? How much is the premium insurance for him or her? You want to have some answer for that customer to give them some kind of reassurance. Make sure that they understand this is based on the model, and the model giving you different kind of outcome based on different factors of these customers. So we can do that now in Driverless AI. So we have the model come out from the previous step, and then we have the examinations to go with the model predictions. Demo. So in this example here, we have some data from the bank, from BNP. So they are all we care about is the outcome is 1 or 0. So it's like whether this transaction here, this claim here is legitimate. So it's okay to just pass through to the next team, or this claim needs to be looked at by humans. So you need to spend more time to look at this claim before you process further. So it's like a binary classification, 1 or 0 in this case. Okay, so let me just go to the software. Okay, so at this moment here, I'm running this software on the cloud. So I'm using one of the good instance. So we got 8 GPUs card on this instance. So it's the what's called the P2 XX large. So trying to run it on the cloud because I don't have GPU on my MacBook. Okay, so this is the first interface. So let me try to make it full screen. Where is it full screen? Okay, let me try again. Control Shift. Ah, okay. Okay, so let's forget about these two now. So these are for different experiments I can serve it on. No, I can't do it. Anyway, so this is the first file that here is like so in this case a simple CSV file from Cargo. So it's a fat file here, but you can always look at different ways to have your different data sets import into the system. So I'm not going to show you that, but this is based on a simple CSV file. But you can use Google BigQuery or Hadoop or SV or Spark if you want to use different data source. So for example, once you have the data in the system, this is the interface for Driverless AI. You can do 3 things. The first thing is a quick details. So I will click on it, and then you have a quick insight into different columns. So it's something very simple that you can do in many other software, but this is something handy to give you some histogram or different statistics of different features in the data. So that's the first thing you do. Not super special, but the next thing is a bit more special because this is the automatic visualizations from Professor Dan Wilkinson. So once you do that, so the user will supply this data set as in CSV in this case, and we will use different algorithms to look at the data set and find out what are the most interesting graph that the user might want to see in this case. So you can imagine that you can put an infinity range of different graphs. You can put a lot of graphs from one single data set. But we're not going to do that. We're going to just give you, the users, the most interesting insight from a new data set here. For example, if you are a data scientist, you may want to look at the outliers. So we will go into the outlier plot, and then we'll go through some of the features. For example, this feature here is called feature V94. I don't know what that is. But it will highlight the outliers in orange color. You can see on the right here. So you can actually click on it, and then it will bring you to the record. So it will bring you to the records that we think they might be outliers for these features. And the user can then decide what to do with the feature. They can leave them in or they can take them out. It's up to the user to do that. And if you want to look for more information about how we create this graph, so we have all the information here. So this is based on a paper from the professor himself back in 1999. So we got all the information here. So just if you want to have a bit more assurance about how we create this different graph, you can go back to the history and look over the paper if you want to. Okay, same for the R graph. So you have a lot of choice of different graphs at your exposures to get some insight into the data set before you build anything. So this is just like the first step that you may do as a data scientist, just look at the data, just to eyeball the data and before you do anything. Okay, so let's say now you're happy with this data set. You're happy with the distribution of everything. You're happy with the outliers. So now you're ready to actually build some model. So I'll go back to the first screen here. So this time I'm going to choose the last option, predict. So this is actually doing the work, the major cargo Grandmaster recipe and all the things happening together in one go. So if this is your first time to use Driverless AI, will give you like ask you, do you want some help? Do you want some assistance? But today you have me, so we don't need an assistant now. Okay, so this is the first screen. So this is what we need to do is we want try to do a supervised learning process. So is that you have some features and you also have the target at the end, so you know the answer before you start. So you want to use that to train the model to learn from the historical data. So that's the first thing we need to ask the users. What is the target that you want to train on? So in this case, it's like convenience because it's also called the column is also called target, but it could be called something else in your case, right? So it's target here. So then it will have a few more options because it figure out that it's a unique value of 2. So it knows that it's a Boolean. It's like a binary classification in this case, and we figure out the best thing for this this problem. At the same time, you have a different option here. You can say, I want to drop some columns here for me. I don't want the ID columns. I don't want other columns that you don't want to use as predictors. So again, it's up to the users. So let's leave this ID here because like this is the ID column that we don't want to use it. But I want to show you that Driverless AI is careful enough to pick this out and to ignore it. So it will avoid some the newbie errors when you do machine learning. So this is if I want to, so if you want to predict some new data sets, so after the model trained, you want to use a model to predict some, make some new predictions. You can supply it with the train of the test data set here, but this is just optional, only if you want to make some predictions. Okay, so now I want to bring your attention to the main 3 numbers here. So we try to make it easy for the users to think about how much time you want to spend with this experiment, or how accurate you want it to be, and how complex you want it to be. For example, the first one, accuracy here, if I can bring you to a document. So I'm going to connect to the document site of H2O. So we have this user guide for Driverless AI. I just want to show you a bit more information about different settings so you have a better idea. So if I go to Okay, so the first number I want to talk about is about accuracy. So it's a very simple, how accurate you want the model to be. So we start from 1, which is the least accurate, to the most accurate of 10s. So what does that mean? For example, if you are running out of time, you want something to be super quick, so you don't care about the accuracy, you just want something quick to give you some quick feedback, you can select 1. So it means it might do a downsampling of the data set. So if you have a big data set like 10 million rows, it will downsample to about 100,000. At the same time, if you don't care about the time that you need to spend, then you can just go for the other end. So you have a really accurate model that uses all of the data. So you can get up to 10 billion samples in this software. And you have also other settings about how complex you want the ensemble to be. Ensemble is a way to combine different models together at the end. So if you go for a simple way to do it, so we don't do any ensemble, for example, level 1 here, so we don't do any ensemble. So the model is okay, but not the best. But if you opt for the complex model, then we'll try to do a lot more ensemble to make sure that it's complex and it's accurate. But at the same time, you have to spend a lot more time to wait for the result. And the other things that just kind of have the different impacts onto the accuracy. So that's the first number here. So the second one is about time. So this is super easy to explain. So this is about the iterations. So again, so if you are running out of time like today, I want to do a quick demo, I'll just choose 1 and then we'll do a few iterations and then I finish. But if you have more time for the experiments, you will try to explore the search base for different feature engineering tricks. So you may find a much better feature engineering set after these experiments, but again, you have to spend a lot more time to wait for that to finish. So again, it's a simple trade-off between accuracy and time for the first two numbers. Okay, and then we have the final thing is about how do you want to interpret the model after you build the models. So what does it mean? So this is like a way to figure out what kind of model you want to include in this experiment. For example, if you want the model to be easily explainable after the experiment, then we will try to use a setting of 10, meaning that we will use some linear model, some model with the monotoxic relationship. So we just go up or down in one way with the target. On the other hand, if you don't care about how to explain a model afterwards, you can turn it to less than or equal to 5. Then you will use all tricks in the Kaggle Grandmaster recipe to create a complex model, but it may not be the best one to explain after the experiment. So these are the three things that we included in the interface here to make it easier for people to think about how much time you have, how accurate you want the model to be, and how much you want to explain the model afterwards to make it into 3 different settings right here. Is that okay so far? Yeah? Okay. So now then we have the now here, so I can now change to 1, so make it like a super quick experiment here. And then when you change it, you can see that on the left-hand side, there's a table here that also gives you some estimate of the experiment. So for example, if you turn it to a 10 for time, then we just do a lot more things and you expect to run it a bit longer. If you turn down the accuracy here, it would do less selection of the model, so we will do something simple but quick. So if you just give me some feedback about all the changes you make to those numbers. So let me keep it to 5 and 1 and 5. Okay. Okay, so here we have the scorer here. This is the metric that you want to optimize for the experiment. So this is a binary classification, so you can use maybe Gini, maybe AUC, area under curve, maybe the actual accuracy, maybe the log loss. So it depends on the need of the business. So this is good for the data scientists to decide what metrics they want to optimize. And then let me just show you one cool thing for the expert setting here. So usually this is done for a lot more users. But for the data kit, you can go to expert setting here, which will give you more control of what's the backend using. So for example, we start with, we automatically include the XGBoost GBM model and the linear model also using XGBoost, sorry. But then because we want to include more algorithm in that to increase the diversities of the final ensemble, so you can turn on TensorFlow model if you want some deep learning to go into the software, to the mix of the models. You can use light GBM if you want to. So these are things that we can allow the users to choose from, so to give them a bit more diversity in the final ensemble. So let me turn it off for now because I want to make it finish it quickly. So I'll just leave GBM and GLM for now. I'll cancel that. So that's the things that we ask the user to provide, some information about what's the target of this machine learning problems, what kind of time that you want to spend on, and then how accurate you want it to be, and then that's it. So you can now say, let's do it, let's go, and see how it goes. So let me just show you a few things here. It will come up in a minute. So a few things is happening, at the same time here. So first of all, you can see this is the first warning here. So what we're seeing is that we find that there's a column called ID column, which is not useful for making predictions. So we automatically take it out to avoid the newbie errors here. So we can close that out. And now it's trying to do something to kind of do some feature engineering in the back end. So what do I mean by feature engineering is that some tricks that maybe you can have the first feature called feature A, you plus the feature B, the next feature together, they create a new feature we call it feature AB. So that could be a more powerful features than individual A or B. So that we call interactions. But there are a lot more tricks that we learn from different Kaggle competitions. So how do we use different tricks to transform the original features into new features? And those are the features that may be more powerful than any of the individual original one. So that's why we're trying to use experiments to test different feature engineering steps. So what you see here in the middle here is some of the features that we generate. So here is the first one here, you can see is just the original feature. So the V50 here is powerful enough as a raw feature, so we keep it as it is. But then we have the second one here. This is like we call the course validations target encoding. So one of the tricks that we use in Cargo to use the target to get some information from the target and feed it back to the features and use that to create new features. So these are some of the like a hardcore Cargo tricks that we use for Cargo. But you don't actually do that like manually for all the features, because in this example here, we have about 133 columns, so about 132 features. If you want to try this trick manually for all the features, like combine different features together, try different interactions, you will spend a lot of time to do that. So we're not going to ask the users to do that manually. So instead, we try to use genetic algorithm to optimize that. So what does that mean? So we try to use a random pool here. So we have a search space defined. So we have different Cargo tricks, feature engine tricks in a random search space. We start with something random. So it may not be very good. We have something random, but we pick the best one in those random starting points and use the best one to evolve to a better set from time to time. So that's why we're saying this plot here. So each dot here is one of the model ran earlier. So what I want to do usually after that is to explain the model. So because I don't want to just give the numbers to the downstream, so I don't want to give some meanings to those numbers to other peers. So maybe your boss, maybe your customers, maybe a colleague. So this is one of the functions in H2O.ai about explaining the model with different informations. So far, this is like a quick summary. So we're saying that these are the most important features, the engineering features, the new features generated from an experiment. And that may not mean something because we're now combining different things together. So we're going to go back one step. So we're going back to a dashboard like this. So this is more meaningful to more business users. Let me just go through them one by one. So for example, if I go to the first graph on the top left, so what we call is the K-line. K-line is like a cluster. So we try to use local model to explain complex model. Let me just disable this. So let's start with this yellow line here. So what is this yellow line? So these are all the points from a training set that we use for training the model. So because it's a binary classification, it starts from a probability from 0 to 1. So it's anything between 0 and 1 here. So we just put them into a ranked order. So I put it on the graph. So start from the lowest point, about 0 to 1 here. So this is just the actual predictions from the black box model in the previous step. The next thing I want to do is to use what we call the line model here. Line is like a methodology to use a local linear model to explain what's happening with the complex model. So we're trying to use a simple model to do the same job as the complex model. But then you can see because it's a simple model, sometimes it can't do the same job or for all occasions. So what we can do now is say we can zoom into one of the points, maybe this one here. Okay, this is a good one here, I guess. So what we're saying that, so we have this point here, this is looking at, imagine it's like one customer here. So this customer, the model predict that we have about 0.972, so 97% chance that this has to be looked at. And then we have the simple model, which we call the line model here on the top. So it's about, you're giving us about 0.982, so similar to the complex models. So what we're saying that in this case, we may be able to use this simple linear model to explain what is going on with the complex model. So how different inputs contribute to the final outcome in this case. So if I click on it, it will zoom in into this customer. Oops, it's not working. Yeah, okay, so take some time to respond. So now when I click on it, it just zooms into this customer here, and I want to look, have a closer look to this customer here. Okay. Yep, so that's what I want to show you here. So of course, I want to zoom in. So now we're trying to explain what's happening with these customers. So we start with the first variable about this customer is about V50. So I don't know what that is, but it's one of the features for these customers. We're saying that this customer, because in this feature, he got a value more than 0.781. So that's the first reason why we go down to this route here, and then we go to the next important reasons is the feature V56. So this may not mean something for you, but if you may measure a different data set with the age, with the gender, with your education level, with that other different information about the customers, they may make more sense to you when you try to explain what's going on with these predictions. And so on, so we can go down to the root and see this is why the model is thinking about a rather high probability of the claim being legitimate or not. And you can use this to get back to your query and say, this is the reason why we think that this customer may or may not have a problem. And more importantly, you can change this graph here, you can translate that into a table. So if I click on explanation here, then it becomes a table that you can use for a report. Let me just zoom it in here bigger. I hope you can see it right here. So what we can see is that this is a table about this customer, your local explanation of this customer. We're saying that because this customer for the variable V11, the feature V11 here, it got this customer got a value of this, and that increased the probability of a claim being legitimate by 2.1 or something. So different value to explain how different things contribute to the final outcome for the decisions here. So this may or may not match with your expectations. So it's sometimes if you talk to the expert in this field, they may not 100% agree with you. But at least this is something, if you can get an understanding between the domain expert and the data scientist, the model building guys, they can get to a common ground to say, okay, I have the model that kind of explain most of your expectation or expected value from different customer, different features from the data. And if they agree with that, they can use this to put it into maybe a report, maybe somewhere that to back you up. At some point, some people may get you to explain what's happening with your model. And this graph, this number here, this table here, may one day save your life. So may someday help you to explain what's going on with the actual black box model that you build. So imagine this model is based on a complex ensemble. So we have different algorithm going into this ensemble. It is almost impossible to give a simple explanation for this ensemble. But this is now giving you one of the ways, one of the leading ways in the industry to explain what's happening with the model outcomes. And you can save it into a PDF, into a CSV file to save it with the model. So together with the model, you have some explanations to go with it. So that is the explanation part. Okay, so let me go back to the deployment part of this. So this is about explaining something to maybe your customers, maybe your boss. But for the people who care about deployment, they will want to look at different things. So I'm going to go back to an experiment that I finished. Okay, so okay, this is still running. Okay, let me just finish this. So let me again show you one of the experiments that I finished before. So this should be the screen that you expect to see after the experiment is finished. So this time I'm using a different metric here, using I think I was using log loss here, so the lower the better. So it's still giving me a better model, but a different metrics. So what I want to show you here is these options that you can have after you finish with the experiments. The first one is what I just showed you about explanation. So if you click on that, it will build all the K9 model for you to explain the results for you. And then if you're interested in scoring on a different data set, so you have some new data set coming into the system, you want to make some predictions, you can do that using the web interface here. If you want to transform the data set, meaning you want to transform the raw features into the new features, the cool new features from the experiments, you can do that. So it will become some new features that you can use it to train your own model. If you don't have the model from Driverless AI, you can do it your own. And then, so the other thing is the pipeline here. So we got different options here. So if you want to stay in Python for the whole thing, so you can just use Python pipeline. So you have a single virtual environment that you have this pipeline built in. So including all the feature engineering and the model scoring in one pipeline in Python. But mostly we will recommend using this we call the module, is the model optimized Java object to put it into productions, because this is super fast in terms of doing all the feature engineering and scoring in one step. which I will show you in a bit. And you can also download like a summary, what we call like an automatic report for these experiments, saying that, so who did the experiments, what kind of feature engineering is involved, and all sort of things here. So let me just show you what's like in the report. So let me go to desktop. So when you download the summary, you have a zip file that when you extract it, it will become something like this, and then you will find lots of different files that just give you all the information at the back end. So what happened with the experiments? If you got all the log files for those experiments. But for the business user or for data scientists, the most interesting part is the PDF, the report.pdf, because it's like a super cool report that we generate automatically after the experiment. So let me make it bigger. Okay. So nothing super fancy, but super useful information about the experiment. So we start from the date. So we got Joe did this, and then you look at somebody like what kind of metric you use, what kind of settings that you use for this experiment, so on. And if I keep going on the more interesting part, so this is giving you some information about the pipeline. So because we have the feature engineering and the model building in one single pipeline, so we just give you some information about that. And then you have the actual performance graph here. Let me just show to here. So this is like a quick experiment. So we were saying that the log loss here is going down, which is what we expected. So we got a better model at the end of the experiment. And most importantly, it gives you some information about the feature transformations that we have. So this is like a peek into the Cargo Grandmaster recipes in a simple table, like so what kind of tricks we use to transform different features from the raw features into the new features. So this will give you some like confidence when you try to bring this whole model out and put it into productions. You know what is going on with the features in the pipeline. And all this is generated automatically with each experiment. So you just run it, and then you have the report here to go with you, as well as the explanation that go with it. Okay. So that is about the report. So the next thing I want to show you is the actual deployment quickly. So I know I'm running out of time. For example, here I got this, what I did earlier. So when you finish with the experiment, we can download the POJO pipeline. So this becomes like a zip file that you can unzip, become something like this. So you have some file like this. So a jar, and then some pipeline, we call it Mojo. So that is all you need to give it to the production team. So this folder here includes all the feature engineering, all the model stacking, and the making prediction step in one pipeline, in one folder. So all you need to do is to give it to anyone, and then you give them an example CSV file. This is like I want to score something like this. So I'm gonna make it good. So imagine this is like the data set that you want to supply to make some new predictions. So different features, all features in a simple way, but there's no target in this file here. So all you want to do is to use this input, put it in the pipeline, let it generate the new features, and do the predictions at the end. And then you can do it with a script like this. So I'm going to show. Okay, so I'm going to use this script here, the one example script. So it's a very simple script to just use the pipeline, look at the CSV, and make some predictions quickly. So let me just quickly show you what's inside. So what is this like? All you need to do is to make sure that you point it to the right Mojo file, so the pipeline. You point it to the input file, could be a CSV, could be other way to have the input. And then you tell this pipeline, okay, whoops. The license file here. So the license file that is, because it's a commercial software, then you also have to have the license files to go with this pipeline to make the scoring. So now if I want to score it, so I just run this sample here. So this is, so all the things are happening in one go. So it's trying to look at this CS file, look at the features that is in that CSV file, create all the new features based on the experiments that you did from the Driverless AI experiment before, and use that to make the predictions and give you the final outcome, which is a number between 0 and 1. So this is the number coming out from the experiment. So you get a different target, so 2 different probability, but you know, this is the outcome that you would expect from a machine learning model. But that step here, that one step here, is also an art of combining different teams together in an automated fashion. So different data engineering team, data science team, production team together in one single pipeline, and it's done with a single software like that. Okay, so I want to give my mate a bit more time. So let me just go back to the slide quickly and to finish off. So we do have a free license for everyone to try. So you can install it on any cloud instance. You can install it locally. You can install it behind the firewall. All you need to do is to go to our website and get a free trial license with your web email, and then you get a license to try it on any hardware. And just one more thing about our event. So you see all the advertisement around you. So it's about our event in London. So it's usually happening only in US. But this year they try to do it in London this time. So we have people, so all the Grandmaster are coming to London. So we have the business users. So we have Booking.com, other people who actually use H2O for the business to come to this event and talk about the use case. So it's not about us talking about H2O. It's about our users talking about H2O and the usage. And then also on the first day, on the training live, you have your chance to actually play with the software together with us. So it's a workshop for Driverless AI, sparkling water, and all the different H2O products in one single, a big room with the whole team working with you together. So that is a really good thing to come if you want to learn more about H2O products. And we're trying to give some free tickets for you guys. So if you go to the website, world.h2o.ai with this promotional code here, you get a free ticket for you and your colleague if you act fast, right? And that's it. That's my talk today. If you want to get a slide, this is the address, and my email is joe@h2o.ai. It should be easy enough to remember. And thank you again, NBN. Thank you.
All right, folks, if you just want to kind of hold yourself for 2 minutes with the iShaft ball just now, yeah. Just literally 2 seconds for a wee bit of a tech handover, and that is us.
Okay.
Rolling? Okay. Good evening, and thanks for the opportunity for me to talk over here. My name is Ashwat. As you can see, I work as a security scientist at H2O, and most of my area that I do is cybersecurity or financial fraud. So I'm usually just looking for bad guys. Quick question, anyone here working in the field of money laundering, financial fraud? Oh, great, okay. So we have quite a few people. Anyone who uses machine learning to work in the area of financial fraud? Okay, again, 2 people. Great. So my talk today will be a slightly high level, primarily because most of the solutions that we deploy, it's a bit difficult to come out and say, hey, this is exactly what we do. I mean, the bad guys are smarter than us, so we don't want them to figure it out. So yeah, so quick, you know, introduction about money laundering. Actually, how many of you guys know about money laundering? Curious. Anyone want to take a stab at it? I mean, I know there are slides out there that are going to come out, but anyone just wants to take a stab at what the idea behind money laundering is? Okay, great. Let's maybe not. So simple idea. You have a lot of black money. You sell drugs on the street. Not saying you guys do. Just saying that, you know, someone sells drugs on the street. You want to wash that. So what you do is you just mix it up with your legitimate money in some form. You actually have like a laundry, you know, and then the money becomes white, just becomes clean. A lot of this money actually comes out from, you know, illegal trade, human trafficking, online gambling, and interesting trade, you know, Silk Route, anyone heard of it? Well, that's the, you know, that's the, I think the Breaking Bad cool part of money laundering. But what are the bad aspects of money laundering? You know, it creates a lot of illegal trade. It negatively impacts society. It also affects governments, you know, where they don't necessarily get all the taxes that they could. California wouldn't have got all the money that it would have got right now because of Mary Jane. Just saying that out loud. And in some countries, you know, alternative existence of power comes in, which is kind of troubling, you know, for the stability of the government itself. So solutions do exist, right? So people who work here, you guys must be working with solutions in money laundering. You guys must be using any of the rule-based systems. You guys want to let me know what do you use, or you can't say that? All right, fair enough. So there are lots of rule-based systems that exist right now in the money laundering space, not necessarily so much in machine learning. And the rule-based systems are the ones that currently, you know, take up the entire space of money laundering. But the issue with, you know, those are, I'll go through some of the issues, but one of the biggest problems that you do face is it's stateless, meaning it does not understand how to capture history and how to, you know, correlate that to an event in the future, which is kind of a big issue. So what do? We up the game, and how do we up the game? We just make the systems much more smarter, and that's where machine learning comes into the picture. So one thing I just want to let you guys know, that the artificial intelligence that we speak about is not the kind of robots that are probably being built there. The space that we're looking at is something called as narrow AI, which means that it's just solving a sliver of a problem. It's just literally one small space of a problem. So that's actually called narrow AI. I think people like Elon Musk and Google are the ones who are taking us, you know, into the broader space of broad AI, but we just, you know, hitting all these small spaces of narrow AI. And yeah, as I was saying, oh, by the way, you guys can interrupt me anytime you have a question or a, you know, a conflict of, you know, assessment. So go ahead. So what we will talk about is how we use machine learning to solve this approach. Now, as I was explaining, one of the biggest issues with the current day AML solutions is that it's rule-based. What that means is if I'm looking at something like structuring, my rule would be as simple as this. It'll say, has this guy done a $10,000 transaction, let's say yesterday? Has he done the same thing today? Is he going to do the same thing tomorrow? If he has done it across 3 days, there you go, structuring. That's about it. Now, the issues with these rule-based systems are, you know, that there is always a person who's sitting at the other end. He's actually analyzing these alerts that get generated, and some of them are actually, you know, positive, some of them are negative. In the sense, some of them are actual alerts, you know, which are valid, some of them are not. I can very conveniently say I have worked with financial organizations right from the States, on the far west, to Asia, and not many of the financial organizations actually have got a good hit rate of anything beyond 20%. So the best hit rate, if you were to get 100 alerts, the best hit rate that I've seen is 20%. Maybe someone might disagree. Are there better numbers that you would see? Maybe not. All right. I've even seen financial organizations where their hit rate is 0.1%, and they say it's good. I do not know under what metric, but that does happen. I mean, probably because of the amount of resources that they've allocated. If they're getting like 10,000 alerts, and if there's one person sitting at the helm of this and trying to solve this alert problem, that is good, purely from a resource perspective. So yeah, we've got a range of 0.1 to about 20%, which is really good. Now that becomes a big issue, because what happens is that when you start getting a lot of alerts across these systems, you have to clear them very quickly. You have to be able to say, hey, these alerts are valid, these alerts are not. And that kind of adds back to all the regulators across the world. So somewhere around 2014, a lot of regulatory authorities kind of came down on the banks and said, look, what you guys are doing is not enough. We guys need you to do much better, use much more smarter technologies, use a lot more science, and make sure you're catching the bad guys. Oh, meanwhile, short story, the bad guys are actually very conveniently moving their money, even now, just saying. So the entire process of how this rule-based system works is you have someone who manually analyzes the data, manually analyzes the alert, looks through all the associated transactions, and figures out if this transaction is actually good or bad. Now, how many of you guys actually have like 3 levels of alert handlers or 4 levels of alert handlers? Do you guys have multiple levels of alert handlers actually? You do. I just paused because I thought you wanted to say something else. No, okay, great. So one of the issues that we also face that I didn't know until 2 years ago is that these different levels of alert handlers have different, different abilities to actually say if this is an alert or not. So to very clearly identify something is very difficult across these alerts. So the other issue tends to be, it's subjective, it's inconsistent, and one of the best rates at which they actually handle alerts is about 30 alerts a day, because they have to actually look through all this data, and it takes quite a lot of time. Still, there is a high false positive rate, because you're churning through this 10,000 records of data and you're trying to remove 8,000 of them, which do not make any sense. And that still exists with the rule-based system. Now, so what we came up with, or the general idea we try to work with, is try to work within the system that exists right now. So we cannot just go out and tell these financial institutions, hey, why don't you guys use machine learning? It does a great job. Just throw out whatever you have. No, that doesn't work, because all the systems that actually exist right now, all the rule-based systems, are millions of dollars, or at least a couple of $1 million worth. And that means it's a huge investment, and the financial organizations has to take a process to actually either get them out, make them better, whatever it is. So one of the things that we actually decided is that we'll use machine learning, and I personally call this machine learning 1.5 for AML, not version 2, because what we're doing here is we're using the idea of building better features across the alerts, transactions, and the customer information, the KYC information for that matter, and feed the same set of features to a machine learning model, and then allow the machine learning model to make a better decision instead of an investigator. And what that comes out is that, what that means is your model 1.5 is purely feature dependent. And actually, how many, yeah, please.
So your pipeline is, you go from expecting the rule-based model, in version 1 is rule-based model, spits that out, people go through it manually.
Yes.
And your 1.5 is rule-based system, spits that out, but then you have a machine learning model to then alert what is, to categorize what you should look at and what you shouldn't look at. Is that's where I'm...
You're in the ballpark, you're right there. The only thing that I'm adding to that is I'm adding a huge bunch of features that would actually add value to validate or invalidate the alert itself.
Okay.
It's literally the same thing, but you're just adding a bunch of features. And the idea behind those features are, features, how many of you guys actually, yeah, yes please.
So just to carry on that, you're learning how to investigate and success the outcomes of the investigators?
Okay, yes, that's a great question. So yes, we are learning how the investigators are investigating the process, but we're also looking at data outside the investigator's analysis itself to identify what could be the features that I could identify as money laundering. So we do analyze like different layers of your investigators to identify what kind of behaviors do they actually capture. And we do it across your level, you know, like level 1, level 2, and level 3, and across the entire investigator space, so that we are not necessarily statistically biased.
I mean, so you're looking at different interventions by the investigator, so whether he's going to block the card or he's going to investigate, what sort of intervention?
So mind you, this is money laundering, not fraud. So two different spaces. But yes, we do look at how they rate a certain case as probably a money laundering case or not. Yeah. Any other questions? No, okay, great. Yes.
What's the incentive for a bank to introduce proper money laundering identification? I mean, there's no financial incentive, is there? Fines.
There, yes.
I think what the industry standard is 20%. Then to raise it to 80%, then what's the...
Oh, so the thing is, in the long term, there is a huge profit in doing this. I'll tell you just right after, but in the short term, the banks actually have a lot to lose. Did you recently read about the $900 million fine on ING? So that is the kind of things that banks face. And that's you know, you kind of don't want to lose $900 million. So at least as a financial organization.
If the industry level is so low,
yeah, so the thing is, I think it's always, you know, a subjective debate between your regulatory authority and the financial organization. The regulatory authority want to push you to identify everything, but the banks are limited by reality. You know, you can't get so many people. You can't have so many cases at the same time, and you cannot not you know, stop investigating in the middle of something. Like you have to finish every case. I think one of the rules that, you know, across the world, one of the rules that exists is if you have an alert today, the alert has to be closed by the end of day today, which is, I see financial organizations across the world tearing up their hair because that's just impossible with the amount of people that they have. But they still do it, and sometimes it's almost like, okay, I pick A, B, C, and that's about it. They just want it cleared. And that's not allowed anymore because of how the regulatory authorities are coming down on you. So you got to have a much more scientific approach in terms of what you do. So the long term that I was talking about. So what happens when you're building this kind of a, you know, a machine learning approach in the long term is your entire KYC data kind of gets consolidated. What that means is that your next version of machine learning model that you're actually building doesn't necessarily rely on the alerts anymore. It does not look at your alerts anymore. It is purely looking at financial transactions, and it is doing something called as anomalous behavioral detection. And how do I say this? So that is something that we just deployed at one of the financial organizations. It is literally going to skim through in this slide. It's my last slide. We're literally going to just walk over it as if, you know, you don't see anything. I really apologize because I really just cannot put up anything about it. But I have some information which will tell you how it works. And that will kind of help you guys out. So that's kind of long-term advantage. So one of the things about features is, features are like metadata. I mean, a lot of you guys actually have machine learning here. So one of the primary things that you guys do is you build a lot of features. And why do you build a feature? Anyone? No? Okay, I'll answer that quickly. So one of the reasons you actually build a comprehensive set of feature is because you want the model to learn as much as possible about the inherent behavior of the data itself. So you want the model to understand every nuanced aspect of the behavior. Mind you, that does not mean that you are, you know, like perfectly trying to fit every data point, but you're trying to identify every interesting behavior that has a statistical significance across your data. And that's one of the reason features actually make so much of an important part of your data set, or in terms of what you feed the model. And the algorithms actually capture the information that the features actually give. So that means that the algorithm is much more tuned to your data. You can almost look at feature engineering as a form of a language translation, between your raw data and your algorithm, which means that it's tuning much more, significantly based off your data. That means your model is much more accurate in identifying the behavior that you want. So do not think of it as overfitting, but of course you can have hyperparameter controls, where you can prevent overfitting, but it's more about trying to identify every interesting aspect that exists in your data. So to be, this can't be any more, the data set, interestingly, can't be any more generic. So the kind of data that we actually take for building our models are transactions, because we're looking at transactions. We're also looking at account information. So what is like the last address of the account holder? Has he had some kind of a relationship with another account holder? There are things like which identify a family as one and stuff like that. Then of course we take the alerts. In terms of account information, we also look at things like LexisNexis, where we try to see if the person actually has a criminal behavior, has he defaulted ever, is there other interesting kind of information that we have. I think I have that in a previous slide. Let me just scroll back a second. Yeah, so we look at the LexisNexis data as well, but we interestingly have, this is something that the analysts actually do. They look through LexisNexis. We also look at some of the card transactions to see if your credit card tends to have a high value of default, but the cards are actually weighed down a bit because it's not necessarily valuable when it comes to money laundering. Not many people do money laundering through cards, but there are cases. International especially, so how would I look at a feature? Bless you. So most of the features that I actually build are a function of time, because what we understand is a person's criminal behavior tends to be a function of time as well. So most of the features that we actually build are a function of time. Here I'm giving an example. Here I have a rolling average across 7 days about a person's balance in their account. So this is just one of the features that we tend to look at. And the reason why we look at features across a period of time is also because when I feed this feature into the model understands that it doesn't necessarily consciously understand that it's a function of time, but it understands the value of the distribution of the data that I'm actually providing it. So you have these huge periods of not any interesting activity, and then sudden spike. For example, if you're looking at structuring, sudden spike in the data, and that could be captured. Now, one of the things, I'll actually take an example of a rule-based system. So I just mentioned to you guys earlier that the way structuring is decided is, if you're about 10,000, let's say for 3 days, boom, you have a flag. Now, what if the person who is transacting transacts like $9,999, right? That clearly misses the rule systems. There are some rule systems which will say, oh, I'll kind of take 1% on that side and 1% on this side. You don't need to take on the higher side, my apologies. You take 1% on the lower side and they'll say, let me capture it. But that still doesn't necessarily identify people, who are just sliding under the bar. I could be moving money at, let's say, $9,500. I've never done it, I'm just saying it. So even those kind of behaviors, because it's a spike in your distribution, it tends to get captured. It tends to upvote your model and then say, look, Bob, this is what you need to find. And which is why these kind of features are actually very valuable when you're looking at money laundering or fraud or any of these things. So some of the advantages of the features that we build. So most of the features that we look for looks at the transactional behavior. I just gave you an example of one feature that we build. Some of the times we also look at what is the time that you spend at each address. This is a very KYC related feature. What's the average amount of days or months that you spend at every given address? How long, and this period of time that you spend at every address is kind of weighed up or weighed down based off how long your history is. Like let's say you've been living somewhere for 40 years and you've changed only 2 addresses. There's a stronger weight for us to understand that, rather the model to understand that you're not necessarily, an interesting person from a money laundering perspective. And that could weigh you down. Mind you, the bias, or rather the assumption that I have with the data doesn't necessarily happen with the model. I just gave an example where I said, if you've lived at an address for 40 years and you've changed your address twice, I wouldn't think you're a criminal, right? But the model doesn't think so. We've had cases in Europe, sorry, it's the same thing, in eastern part of Europe, where people have not moved from the location where they were born, and they were actually making a lot of transactions which was clearly money laundering. So the model is, it's not necessarily subjective, it's pretty objective in its approach. And some of the things that we do as we look at features as a function of time is that the features are continuously being tracked. Your behavior is constantly looked at as a function of time, which is very interesting, which means that a lot of information is being fed into the model. This kind of scares me a bit as well, because this means that the model knows a lot about me, but I'm still okay with it. The rule variables can only identify threshold changes. This is something that I just told you guys about, right? Like when you have a rule, when you have a rule, for example, structuring, it's only looking at changes in thresholds. It's not necessarily looking at, a change in the slope or any such thing. And that's where kind of the issue comes in as well. So that's the advantage of, looking at features for the modeling technique. So the way we usually deploy the model at most of these organizations is there's a simple model. Joe earlier talked about, the Mojo or the Pojo. The Mojo or the Pojo basically gets deployed at different locations, across an organization or at terminal nodes. We have all the alerts being fed in and all the additional data that we need to make decisions on fed into this machine learning model as well. And then you actually get an output where it's, it says whether it's suspicious or not suspicious. And it gives us a pretty good result. Now, the thing is, so the advantages of using this approach is, we're using AI, so which is kind of cool, at least from a name point of view. The features are very consistent, things are very objective. We have quick classification. So at the peak speed, our model has actually been able to go through 1.6 million alerts. It has been able to classify 1.6 million alerts in a second. So that's the speed at which the model actually, kind of classifies your alert, provided all the data that is required is ready and fed in. It's got really low false positive rate, and it's tweaked based on your risk appetite. Now, I'll pause here for a moment. And I'll talk about the risk appetite. So different, financial institutions work with different kind of regulatory authorities. I would say that the United States is super progressive in the way they allow newer technologies to be involved, at least in a testing phase. But I would say, like, let's say Western Europe is kind of still limited in the way it looks at, newer technologies being brought into the model. So what happens here is a lot of regulatory authorities want a clear-cut explanation about what the model is doing. What that means is that you have to very clearly tell them the the decision path that was taken to classify an alert, a yes or a no. So one of the things that we insist on when we build the model is to use random forest models. And the reason why we use random forest models is because random forest model 1 works really well when it comes to noisy data. You would assume that bank data is really good, super hygienic. Not necessarily the case, because you have to bring in data from many different sources. That means you are mucking it up, and that means that the data can be like super noisy. So we use random forests, and we use a tree-based approach because when we use a forest-based technique, that means you're using decision trees to make some kind of decision for your alert. So that is something that we've been very successful with across regulatory authorities. We have said, look at this tree, this is what this alert is being classified with, this is how it is, and they're very happy about it. Now, the risk appetite, the other part of the risk appetite is much more towards your financial organization. Now, how much of false negative rates do you guys want to observe? Now, if you guys know, in a machine learning model, you have a confusion matrix, right? You have your true positives, true negatives, false positives, and false negatives. Now, your false negatives are the ones that actually cause the biggest issue across the board. Anyone have a number on their false negatives that they have to work with? Maybe not. Okay. So I'll throw out an example. So one of the false negatives that I actually have to work with is about 0.25%, which might seem okay, but when you're tuning a model with, let's say, 92% AUC, and you're trying to tune out, retaining an AUC as close as possible to 92%, keeping a false positive of 0.25% is super crazy. It's kind of a pain. So when we have to work with that kind of a risk appetite, what we tell the financial organization is that if all your risk if the maximum amount of appetite that you have for your risk is 0.25%, then this is the maximum amount of true positive rate that we can actually give you in the model. This is the best that we can do in terms of classification of your alerts. So that is something that the financial institution needs to look, it's most of an introspection for the financial organization, where they have to look in and say, what is the best number that we can deal with? What is the most comfortable number that we can deal with? And that's what the risk appetite and the low false positive rate actually deals with. We've had, at a false positive rate of 3%, we've had accuracies as close as possible to 93, 94% in terms of, false alert classifications. So that's kind of a good thing. But that means that the financial organization was ready to manage a 3% false negative rate. For some, that can be unthinkable. It's completely out there. That's something that they wouldn't accept. But for some, that's probably okay, because a 3% false positive or false negative rate is okay for them to deal with their regulatory authorities. So that's kind of very subjective. It has to involve your model, risk officer or any of those organizations to make sure that that works out for you guys. So one of the things that we also do is we try to get the investigator. So the investigator is still not out of the equation. They're still in the system. What we also do is some kind of algorithmic tuning. And if any of you guys have put in a model into production, you know that as new data starts to flow in, you will have a model degradation. Your model degradation rate might be 15 days, 6 months, 2 hours. Could be anyhow. If you're looking at fraud, your model degradation is crazy. You could hit bad area very soon. So you kind of have to figure out your model degradation rate and then bring in your investigator to say, is my model still performing the same way? At that time, what happens is your investigator is sampling out classifications from after the machine learning model has actually classified alerts, and then he's basically feeding back into the system saying, hey, this is wrong, this is right. So we kind of use that classification to further tighten the kind of features, the kind of parameters that we actually put in. Mind you, the H2O models are not online learning models. What that means is that the model doesn't immediately learn that the classifications are wrong and tune itself. It actually has to go back to the system, but because the whole H2O system is a one-click system, I don't think it should be a problem. Maybe you can take a coffee break and you'll get a new model. So that should be easy. So this is the process that we use involving the AML analyst to build a better model. And this, at least right now, is very necessary because it helps us stay in check. When I say us, I mean the guys who are developing the model. It helps us stay in check, not necessarily making interesting models that doesn't necessarily work. And it brings in the domain knowledge as well as a part of the model. So, yeah, okay, so there we go. So the pure data-driven model is what I was talking about. So earlier what I talked about is the kind of solutions that we have deployed across financial organizations, which are working right now. But what, for the past 1 year that we were working on was this thing called the pure data-driven model. Now, the idea, I'll just explain to you the idea of what the idea behind the pure data-driven model is. The feature-based model allows us to play in this, sandpit, which is basically described by the rules of existing system. You use FCRM, Fiserv, Actimize, any of these things. It allows us to play within the rules that are described within the system. Now, what happens if there is a new money laundering behavior that the rules haven't yet captured? If there is something, out there, something that's new. And that is where we started working on the pure data-driven model. The idea here is to not use the alerts. I think that's probably in the next slide. Yeah, so the idea here is to not use the alerts, but use all possible information about a customer, his transaction information, account information, card information, and that is my fault. That has to be an anomaly detection algorithm, not a deep learning model. That's my mistake, my apologies. And we designed an anomaly detection model on top of it, which can tell you what is probably suspicious and what is not probably suspicious. So it's got a huge probability factor associated with it. Now, in this case, it's not as easy as binary classification, where 1 meaning it's a bad case, 0 meaning it's a good case. Here you kind of have to do a lot of tuning, because if you're using autoencoders or if you're using k-means is my favorite, so I use that a lot. If you're using autoencoders or k-means, you kind of have to identify the space where with the highest probability your transactions are actually suspicious or can be associated for money laundering. And that tuning is a lot of R&D. What that means is you have to work with the guys who know business, and you have to find out which space in terms of the output that you've got actually helps you classify the maximum number of transactions as anomalous or as money laundering. So once that happens, then your transactions, account information, card information can go into the model, and then you can identify what is suspicious and what is not suspicious. This again follows the same pipeline, where an investigator is actually sitting and analyzing at the end of the road to see what the anomalous behavioral algorithm is actually right or wrong. And that's kind of the advantage that we have. So this is our last slide, basically. So the idea behind this is the algorithm understands malicious behavior much better, and it is much more smarter to work with features than necessarily to work at a specific target. It does not need alerts anymore for training, so pure anomalous behavioral model. We kind of get deeper insights about our customers. So interestingly, one of the financial organizations that we deployed it with uses this model to build a KYC information database, which is being now further used for sales and marketing as well. So you can kind of figure out where all you can go. So I'm kind of done. Any questions? Anything at all? Yes, please. Thank you. Yes.
So do you have any central repository? Say you have a deployment for Lloyd's version and a deployment for Masshaven, and Masshaven identifies some new money laundering practices. Do you have anything that can then model that particular behavior and feed it back into the central repository that then goes out to the banks?
I think I can answer that question. Our CEO is actually building something like that right now. I mean, he's not coding it, he's trying to get the organizations to work together to make something like that, where every model is actually sending back some information where there is, every other financial organization can learn from it. But what we're actually trying to work through is the aspect that what, let's say, you send out, and let's say something else the Royal Bank of Scotland is going to ingest, or ING is going to ingest, or Bank of America is going to ingest, is not necessarily something proprietary that you did not want to send out in the first place. So what we're working through is a lot of filtration process where it's purely technical information about the behavior and nothing else about the kind of behavior that your bank might very frequently see. So it's kind of a very thin space, so we have to be very careful about it, because at the end of the day, we don't want someone coming and saying, oh, your bank, you guys laundered a lot of money to Cayman Islands. No, you definitely don't want that kind of a badge. So it's kind of a difficult thing, and we're still working through that space. Yeah.
One of the hot topics now in ML is graphs.
Yes.
So for anomaly detection, that's a very interesting approach.
Yeah.
Are you looking at that for you?
So when I did my PhD, I actually could not get my access to any kind of a graph system. So I had to build the entire system without graphs, but it looked like it was always graphs, which means that the database had to look like a graph, but I never used any graph models. So what I kind of did was I turned the model into a node and an edge problem the same way, but I made, the idea was every node is either a transaction or an entity, and then every edge, every kind of feature attribute that's associated for a node is actually the features that's associated for it. So the same model right now we're using is something called as smurfing, where we're not necessarily using a graph approach, but we're using the same kind of methodology, and we've actually had tremendous success in Western Asia. Sorry, trying to figure out what to say. Yeah. Okay. Any other questions? Yes?
So, if I understand well, those methods which are not feature-based are clustering-based, right?
Yes and no. They still need features. So one of the things is when you do, the first aspect that we did, the feature-based approach, is something called as a supervised learning, basically meaning you tell the model what is your end outcome. In the second approach, you don't have a target, meaning it's an unsupervised approach. They still require features, but what you have to actually do in that approach is you have to tell the method, one, you have to give it a comprehensive set of features, meaning you kind of literally have to overwhelm the model with a lot of features in every aspect that you would want it to identify. But then you also have to tell the model how to discretize the space, meaning like how to break down, how to value certain features and how to not. So the features are still going into the unsupervised space, or the unsupervised modeling approach. But now you have to tell the model what is important for you or what is not. So you can do it by weights, you can do it by elimination, you can do it by like a rule that you put in saying this feature is actually very important. The third one that I mentioned about, putting the rule, I kind of don't like it because we're going back to the old system, where you're saying, no, feature A, you're actually important. Because we kind of have to allow the model to discover on its own how the space works. So I would say the first two methods are much better.
How does that work for explainability? So are we able to
So,
how exactly
yeah, so now the question is, the way they're actually verifying it is they're using that output and they are analyzing the same thing when the same data is actually run through a set of rules. So you have one, you have one model which is actually doing the unsupervised approach and it's giving you some transactions that are suspicious. You have another model where the same data is actually going through your rule system, then going through your supervised ML model, and it's actually putting out your classification. Now, the way they analyze it is they analyze the output of the unsupervised and the supervised, and they say whether it's, is it capturing a good amount of the data? Is it not capturing a good amount of the data? So it's by surrogacy that we actually have to say whether this is good or not.
Have you tried deep learning then combining with something that's supervised?
So
My mind like the logical thing, but it's hard from the point of
it's super logical, very fair question. So the issue with deep learning is you kind of have to explain why you stacked up so many kind of layers, why a certain edge is actually heavier than another edge. It's really difficult to explain it to someone who, from a regulator, who wants to understand what's happening here. But it is still doable. It does not mean that you can't use deep learning. But essentially, if we can't explain why an edge is of a certain weight, it really becomes difficult to tell an investigator, hey, just look at this black box. It works great, but we don't know how it works. That's the issue. Yeah?
So when you're using supervised learning, surely your signal data set will only consist of people that have been caught. So ignoring for now the new types of money laundering, how do you then train models to catch those false negatives, which will find closest to the initial transactions?
So it's a given that the false negatives are not going to be caught, at least from the models that we develop. The false negatives are more like, hey, this is the best that the model can perform. So you remember, you will ignore those false negatives is what we do. Now, the issue, using the unsupervised approach, we kind of try to reclassify the false negative to see if they could be caught, but not in the supervised space itself. Like, it's really difficult to do anything with changing the false negatives until you say you have a much wider risk appetite.
It's mostly about false positive reduction.
It's a false positive reduction for the alerts, but at the end of the day, those false positives have to be rightly classified as false positives, right? Yeah. So that. Yeah. Any other questions? Good. Great. Oh yes, please.
So my question is more related to stuff.
I also got.
I actually worked on H2O and some other platforms for my master thesis.
Thank you.
So I used Driverless. I wanted to know more about your data frame because I use your library in R and Python.
Okay.
And I pretty much similar to the same models in Driverless. So I was more focused on the idea of extendability and see to what extent it goes with for, let's say, someone with a good background in the field. And what I mostly noticed is there's a lot of emphasis and focus on a really big understanding of the elements of machine learning, which you have it up here. So if people from industry are using your products, let's say, how do you expect them to first understand your data frames, which runs on Java underneath, right? A key value distributed in Java to then...
So think about what kind of inputs that we require the business users, so without deep data science background. So you know about the data type that they may want to provide to us? Or?
I mean, so you do have, your data frames are different to those which are using R.
They don't care. They don't need to think about that because it's now behind. So what we have is like we have interface to ingest different data source, be it a Google query, be it a SQL, be it a normal fact file like CSV or text file. That is all they need to think about. That is all we think about what kind of integration they do before Java's AI. So come up with a simple table, whether it's on Hadoop, whether it's on Spark, that's their business. When they have that, already in their business organization infrastructure, they link that to Java's AI, and that within that is like what we call the Python version of their table inside Java's AI.
What is that?
Inside. It's not. If you search, we used to have the data table only available in our web, but we have Method and my colleague Pasha to put that into Python. And now we have that version of data table in Python. And we use that as the base of data frame to power everything in Java's AI. But before that, users don't need to care about transforming data into that format. It's all been taken care of when you have the input linked to the Java's AI. So they don't have to transform it in any way.
Okay, and the XGBoost model provided slightly different results depending on whether I was using the library in Python or R. Is there any specific reason?
Oh, so XGBoost is a big library that we only contribute to the GPU acceleration.
Right.
So say, so it's from DMLC, so it's from the research group in Washington, really. And then we have our own contribution as in GPU acceleration. So we don't really have like a complete benchmark of how different versions in different languages, maybe Python or R, we have different results. We only care about what we have in our version, that is the GPU accelerations in our environment, which is only Python for now. So we only have our own versions. We don't have the complete benchmark of the results conversion, whether we put it into R, because the base of this AI is CUDA, C++, and Python. There's no R in this. But that would be the interface of our using Calculate to interact with this software. But there would be no like an R version of XGBoost, so that's no concern about that for now. So hopefully that answers the question.
Okay guys, we're going to call out to, I'm sure Joe and Ashraf will be along for a couple of minutes later to get any more questions. But I'd like to say just thank you very much to Joe and Ashraf. Thank you. Before anybody goes anywhere, we've got Alan here from Product Forge. I'd like to say a couple of words. Alan?
Hi, I'm going to be super brief. I'm from Product Forge, and Product Forge is a community of people who believe in using technology and entrepreneurship to drive positive social change. We are going to be organising Europe's largest health hackathon here in Europe. Europe's largest health hackathon here in Edinburgh in February next year. And if you've not been to Product Forge, we bring together people like you who have an interest in data science and AI and technology, together with people who work in the sector. So we'll have data analysts from NHS Scotland. These are people who are responsible for looking after your health data. Engineers from Canon, who develop medical imaging technology. And a variety of other people from around the tech ecosystem, as well as designers and students and all sorts of other people. We put you in the same room over 4 days to develop new digital product prototypes. So it could be apps, it could be online services, and so on. If you're interested, follow us on Twitter. We're at Product Forge. Our website is productforge.io. Or if you don't like using the internet, then I have flyers. Thank you very much.
Amazing. Cheers, Alan. Thank you. Very last thing. Thursday sees the launch event for DataFest. Most of you know all about DataFest, may have been in the past. Quickly grab your phones, take a photograph of that code, go and use that amazing interweb thingy. Go find DataFest and you can get a complimentary ticket should you use that code there, DataFest 19 launch meetups. Hooray! On Thursday of this week, Thursday the 20th. Very last thing. Say again, mate?
Can we go and meet Kathy?
Yeah. Go and meet Michael. You're over there. Very last thing, if you brought a can or a cup or any kind of drinky thing in with you, can you please take it outside and either put it in the bins there or in the big black poly bag, because we ain't your mammy. Thank you very much. See you later, folks. Bye-bye.